Collision theory. Collision theory is a theory that looks into what are the factors on which the rate of a reaction or a speed of a reaction would depend at a molecular level. So the basic principle behind the collision theory is that in order for a reaction to occur, the particles must collide with each other. And the number, if we can increase the number of collisions that are occurring over time, we can basically increase the rate of the reaction. Any way we can increase the number of collision, that simply means we are increasing the speed or the kinetics of the reaction. So there are some factors for every collision so that the collision should result into products. That is one, the collision, the reacting species should collide in a particular orientation that allows contact between the atoms that will become bonded together in a product. So they should be in correct orientation. The next is this collision should have adequate energy. So when they collide, if they do not have enough energy, there is a threshold energy that atoms should have. So whenever they collide, it should be above this threshold energy. Only then they can result in product. Otherwise, these collisions are fruitless. Basically, they collide, but they do not produce any product. For instance, for any reaction to occur, if A is changing into B, it does not occur directly. It usually follows a path that looks like this. For instance, if this is the energy of your energy of the reactant in the beginning, and this is the energy of the products, usually for a reaction, the reactants need to gain a very high amount of energy, reach a particular state, and then they'll get back into product. This state where the energy of the reactant is the highest is called as the transition state, or this is also called as the activated state. And the reason being that here the energy is really high, that simply means the molecules are activated. So we also call it activated state. The energy that is needed to increase the energy of product from this part up until the very beginning on top, that is called the EA, which stands for activation energy that is needed to activate the reactant molecules. That is called the activation energy. So this is EA for forward reaction. This would be EA for reverse, which means if the reaction is happening reverse. So if this is my reactant converting into product, the amount of energy it needs to go from here to this part, that is called the reverse reaction, EA. And the difference between the energy of reactant and energy of product, that you might remember from thermochemistry, is called as the enthalpy of a reaction. So this is delta H of reaction. Now in this case, because energy of your reactant is lower and then the energy of product, which simply means reactants are absorbing energy to turn into this, they have to go from here to here. So they are going to absorb energy. Initially they have less energy, finally they have more energy. So energy absorbed is an endothermic reaction. So this is the energy diagram for endothermic reaction. This is potential energy on the y-axis and reaction progress on the x-axis. We can also use time on the x-axis. That would still give you the same graph. Even if the reaction is exothermic, we still need to have or reach an activated state in case of molecules. For example, if this is the energy of reactants and this is the energy of products, overall the energy of the system is decreasing, which means this is delta H is negative, which is exothermic reaction. But it still needs to reach this threshold value, only then it can cross the barrier and convert into product. So even in this case, transition state is going to be high in energy, higher in energy. So this is the same thing explained energy diagram, energy level diagram. This is also called, this is the energy on the y-axis and the reaction progress or time on the x-axis. If reactant is turning into product, it would look like this for an exothermic reaction. So you should be able to recognize the graph. If it's exo, endo, where's EA? what is activated state. This theory, where the reactant needs to reach a high energy state in order to turn into product or a transition state, is called the transition state theory, which simply tells you that an effective collision between particles leads to formation of a transition state or an activated complex. The transition state is very unstable species which contains partial bonds, and that is why this state, whenever the molecules reach here, they quickly turn into products because it's not a very stable state. This transition state cannot be isolated. You cannot separate it. Either the reactants are found or products are found, but the transition state cannot be isolated because it's very unstable. As soon as it's made, it is converted very quickly into products. And the amount of energy that is needed to reach that activated state is called the activation energy. When particles collide effectively, they reach an activated state. The energy difference between reactant and activated state is activation energy. So if the EA, which means if this is the EA, this is how much energy is needed for reactant to turn into, just get into activated state. This is called EA. If EA has a smaller value, which means instead of having this, if the EA is just this, the reaction will go a lot faster. The lower the activation energy, the faster the reaction. So that would increase the speed of a reaction. Another factor that increases the change or that changes the rate of or speed of a reaction is temperature. Most of the times, if we increase the temperature of a reaction, the reaction usually goes faster, which means it increases the speed of reaction. And the reason behind that is because the molecules again are trying to reach activated state. If the temperature is high, the molecules are not starting at this level, they're already starting at this level. So now they only need to cover this much of distance, which means when we work at a reaction or we perform a reaction at a very higher temperature, that just means the reaction goes faster because there is more number of molecules that have higher energy that they can cross the threshold. At higher temperature, the fraction of collisions with sufficient energy equals to or greater than EA increases, and therefore reaction rate increases. For example, this is an example showing that same approach. Important thing to remember, whenever the temperature changes, the K increases. K does not change at any other given point except when temperature changes. So if the temperature is higher, rate constant will also have a higher value. How can we calculate the activation energy? That is given by Arrhenius equation, which is this. Arrhenius equation is K is equal to AE to the power of negative EA over RT, where EA is the activation energy. So if we are given an equation where we need to solve for this, you just use this equation, find the missing information. Most of the information will be given to you in the question. Another way we can use this equation is we can rearrange this equation into this format, which is ln k equals minus EA over R 1 over T plus ln k. If we use this equation, we can make a graph ln k versus 1 over T, where your slope will be equal to minus E over RT. Again, y equals mx plus b. So this can be used, this information can be used to solve for what is activation energy or K, depending on what information is given to us. Also, there's another equation that is used if we are interested in figuring out what is the rate constant at two different temperatures. We can use this expression where K1 is the rate constant at time T1, K2 is the rate constant at time T2, where T1 and T2 are just two different temperatures. So we just use this equation to solve for whatever the missing information is. Example, the decomposition of hydrogen iodide has a rate constant of this much, so this is the rate constant, so this is K at 500 Kelvin. This is my T, and this is the rate constant at 600 Kelvin. So this is the new K, which is K2 at T2. What is EA? So if K1 and T1 is given, K2 and T2 is given, we just have to figure out what is K, which means we will have to again rearrange the equation that we just saw. Important thing there is temperature should always be in Kelvin. So we will use this equation again. Ln K2 over K1 equals minus E over R1 over T2 minus T1. Plug in all the values and we just rearrange the equation and solve for EA. Another example, you can give it a try again on your own. Calculate the activation energy, so we just have to solve for EA. For decomposition, given the following values of rate constant, K1 at this temperature, K2 at this temperature. Again, we just rearrange the equation to solve for EA, and the equation is this, which you do not have to memorize. It will be provided to you in the formula sheet. Last concept here is the molecular structure for understanding the rate of a reaction. Whenever a reaction occurs on the molecular level, what is happening? For the collision between particles to be effective, it must have sufficient energy. It should be correct orientation. We saw that before. And this is the equation that we can use to calculate Arrhenius equation, where A is basically the frequency factor. Another factor that affects the speed of a reaction is called a presence of a catalyst. A catalyst is basically a substance that increases the reaction rate without itself being consumed in the reaction. Any substance that if I add to the reaction, A is changing to B. If I add something to this reaction, let's say C, then the reaction will start going a lot faster. Then this C is called as a catalyst. It is not used up in the reaction. If I start with 1 grams of C, at the end of the reaction, if all of it is converted into B, I would still have 1 gram of catalyst left. So catalyst is not involved in the reaction. It is not, the concentration does not change. But what does it do? It lowers the activation energy of a reaction, and that is why the reaction goes faster. For instance, if let's say this is a reaction, A is changing into B like this, and this is how much is the activation energy needed originally. If I add a catalyst, the reaction, it reduces the activation energy to a little bit lower. Nothing changes. This value is still the same, this value is still the same, but now the activation energy is a little lower, and that's why the reaction goes a lot faster. A catalyst will speed up both the forward and reverse reaction, so this would speed up, and the backwards reaction will also speed up. But it does not affect the delta H. So you can see here what is delta H. Delta H is this. Same thing here, delta H is this. So delta H is not affected. What's affected is the overall how fast the reaction occurs. The last part we'll talk about is called reaction mechanism. Mechanism basically of a reaction is the sequence of single reaction steps that make up the overall reaction. For instance, if A is changing into D, it's not necessary that reaction occurs directly. We could have A changing to B, B is then changing to C, whatever C is produced, that eventually changes into D. So this reaction that we saw overall, this is the overall reaction. It actually occurs in 3 steps. So this is step 1, step 2, and step 3. So it occurs in 3 different steps, and this is called the mechanism of the reaction, which explains every single step that occurs from starting from reactant to product. A lot of times if we write the rate law, it does not look like we usually do not write the rate law like this. Rate law is K A to the power of X. It's not necessary that the coefficient for A is X in equation. Why is that? Because this rate law depends on one of these steps of the three. The rate law does not necessarily depend on the overall reaction. It only depends on one of these steps, and that step is called as the rate determining step. For instance, if in the out of these three steps, if I say the slowest step is step 2, that means the rate determining step is also step 2. In this case, then the rate law will simply be K to the power of B to the power of 1, concentration of B to the power of 1. Why? Because in this case, this is the reactant. It does not depend on A, it does not depend on C, it only depends on B. Another thing is, in lot of reactions, we also define the reaction based on molecularity. Molecularity means how many molecules are participating. For example, there's only one molecule, it's unimolecular. If there's two molecules, it's bimolecular. That's when the reaction order becomes 2. If it's bimolecular, could also be like this. There's two different types of molecules. So it's 1, which means overall order is 2, so bimolecular. And then term molecular stands for 3. Again, the slowest step in a reaction is a rate determining step or rate limiting step. Why? For example, in a relay race, if in the relay race there are 3 players who are participating as one team, the final result for this team, if they win the race or if they do not, depends on the person who is running the slowest in this relay race, right? So that's the same example here. In case of kinetics, if there are 3 steps, step 1, step 2 and step 3, the rate depends only on the slowest step. For example, if this is a reaction, NO2 plus CO gives NO and CO2, and the question is asking what is the rate law for this reaction, we have to look at the mechanism of the reaction. So let's say the reaction mechanism is these two. It's given to you in question. This react step number 1, step number 2. And it tells you that the first step is the slow reaction, which means that is the rate determining reaction. So the rate will only depend on reaction number 1. Now I can say rate is equal to K reactant 1, which is NO2. Reactant 2 is also NO2, so that's 2 NO2, which means NO2 will get squared. This is the rate law for this equation, overall equation. It only depends on one of these steps, which is which is the step that is the slowest out of the all. Example question could look like this. The following elementary reaction are proposed for a reaction mechanism. This is fast, this is the slow step, this is the fast step again. Write the balanced equation for overall reaction. We simply add all the 3 reactions. Adding simply means I would write all the reactants on one side, all the products on the other side, and cancel the same reactant and products that are present on both the sides of the arrow. That would give us overall reaction. For example, in this case, the reactants are Cl2 plus Cl plus CHCl3 plus Cl plus CCl3 gives us this 2Cl. So you can write Cl plus Cl, or you can just simply put as 2Cl. We'll put it as 2Cl to avoid any confusion. So we can get rid of this. It will produce all the products, which is 2Cl plus HCl plus CCl3 plus CCl4. Now we cancel everything that's common. For example, this is 2Cl, this is also 2Cl. Reactant side, product side, you cannot have the same species on both the sides of the arrow, so they cancel each other out. CHCl3 here, CHCl3 is nowhere else to be found. CCl3 here, CCl3 on this side as well, which means this also cancels out. So the overall reaction is Cl2 plus CHCl3 gives us HCl plus CCl4. Now Determine the molecularity of each step. This is one reactant, so it's 1 unimolecular. This is 1 plus 1, so this is bimolecular, and this is 1 plus 1 again, so this is also bimolecular. Write the rate law for each step. For this, rate law will be rate is equal to K, concentration of reactant to the power of whatever the coefficient is. This would be rate is equal to K, because this is each step, so the rate law can be written based on the coefficients. Otherwise, we usually don't use a coefficient. It has to be determined experimentally. This will be Cl, this will be CH, Cl3. The next would be rate is equal to K, Cl to the power of 1 and C, Cl3 to the power of 1. That's for each step. What is the rate law for overall reaction? Again, overall reaction only depends on the slowest reaction. So because this is my slow reaction, the overall reaction rate law is same as the rate law for this particular reaction. So this right here is my final answer for D. Another example is like this. The reaction mechanism that has been proposed for decomposition of H2O2 is this. So this is the slow, this is the fast. What is the expected rate law? Rate law will only depend on slow reaction. So it would be rate is equal to K, reactant 1, which is H2O2 concentration to the power of 1, because coefficient is 1, times I minus to the power of 1, because again coefficient is 1. So the rate law would look like this, because it only depends on the slow, it does not depend on the fast reaction.